Hello children. So start the next topic of the chapter P block elements, that is the group 16 elements. So children, in the group 16 it constitutes of the elements oxygen, sulfur, selenium, tellurium and polonium. So these are the elements of the group 16 and these elements are collectively known as the chalcogens. Chalcogens, and this means that ore forming elements. Basically the ores are existing in the form of oxides and sulfides, and these oxides and sulfides are present in the group 16. That's why the elements of the group 16 are named as the chalcogens. So the elements except polonium are non-metallic. Selenium and tellurium, these are the metalloids. They show the metallic as well as non-metallic character, whereas the polonium has the metallic character and it is also an radioactive elements. So after that children, the atomic properties of the group 16 elements. So what are the important atomic properties in this? The first is electronic configuration. So basically the group 16 elements has the valence electronic configuration NS2Np4. Okay, so this is the valence electronic configuration. Here N is the number of cells. After that, the next important property is the atomic and ionic radii. So children, as per the rule, it is known that the atomic radii increases down the group due to increase in the number of cells. So as we move down the group in the group 16, the atomic and ionic radii of the elements will also increases. The atomic radii of the group 16 elements are smaller than the radii of the group 15 elements. Next is the ionization enthalpy. Ionization enthalpy, and as we know that the ionization enthalpy has the inverse relation with the atomic size. So since the atomic radius increases down the group, so that the ionization enthalpy decreases from oxygen to polonium in the group 16, and this is due to only the increase in the atomic size down the group. So children, however, the ionization enthalpy of the group 16 elements are lower than that of group 15 elements. Why the ionization enthalpy of the group 16 elements are lower than the group 15 elements? And for that, the only important reason is in group 15 having the electronic configuration, that is the Ns2Np3. That is the half-filled electronic configuration is present for the group 15 elements, and due to this stable electronic configuration, the group 15 elements are highly stable, and this is the reason only for that the ionization enthalpy of group 16 elements are lower than that of the group 15 elements, due to that the half-filled electronic configuration, and that half-filled electronic configuration of the group 15 provide extra stability for the group 15 elements. Next important property is the electron gain enthalpy. Electron gain enthalpy means the amount of energy released when a neutral gaseous atom gain electron. When a gaseous neutral atom gain electron, the amount of energy is released. That energy is named as the electron gain enthalpy. So the electron gain enthalpy of oxygen is less negative than the sulfur, and this is due to the compact size, that this is due to the small size of the oxygen atom, and due to which there is the greater inter-electronic repulsions are found in the oxygen atom, and from oxygen onwards the electron gain enthalpy become less negative up to polonium. So this is about the electron gain enthalpy. Next is the fifth important property is the electronegativity. Electronegativity means the tendency of an atom to attract the shared pair electron towards itself. So in the group 16 elements, the oxygen has the highest electronegative value after the fluorine atom, and electronegativity decreases down the group due to increase in the atomic size as we move from the oxygen to polonium, and this indicates that the metallic character also increases from oxygen to polonium. Next, sixth property is the catenation. Catenation is the self-linking property of the elements. That is, the elements having to self-link with one another. That property is named as the catenation property. So, in group 16, only sulfur has a strong tendency of catenation. Oxygen show catenation behavior less than the sulfur, and because the oxygen has very small size, due to the small size, the oxygen experiences repulsion between the lone pair of electron as well as the oxygen and oxygen bond. So, due to the repulsion, inter-electronic repulsion as well as the repulsion between the bond pairs in the oxygen-oxygen atom, the oxygens show the less catenation behavior than the sulfur. So, these are the important atomic properties. After that, children, we move to the next, that is the physical properties. Next is the physical properties. And in this physical properties, the first important is the physical state. What are the physical state of the elements which are present in group 16? So, the oxygen, as we know that the oxygen is a diatomic gas, while the other elements are octa-atomic solids. For example, sulfur is existing in the form of S8. Next is the metallic character. Next important is the metallic character. So, children, the metallic character, as we move top to bottom in a group, the metallic character of the elements are increases, and so that the oxygen and sulfur are non-metal, selenium and tellurium are metalloids, while polonium is a short-lived radioactive metal. Next is the allotropy. Allotropy, and in this, all the elements of the group 16 show the allotropic nature. They exist in more than one form. And next is the metallic melting point and boiling point. Melting point and boiling point of the group 16 elements. So, melting and boiling point of the group 16 elements increases down the group with increase in the atomic number as we move from oxygen to tellurium. So, polonium has lower melting and boiling point than the tellurium. Oxygen is a diatomic and sulfur is the octa-atomic solids, and therefore there is a large difference is found between the melting point and the boiling point of oxygen and sulfur, because oxygen is existing in the diatomic gas form, whereas the sulfur is existing in the form of octa-atomic solids. That's why there is a large difference is found in the melting and boiling point of oxygen and sulfur. After that, children, we move to the chemical properties of the group 16 elements. And the chemical property, the first important thing is the oxidation state. First is the oxidation state. What are the important oxidation states of the group 16 elements? So, elements of the group 16 exhibit a number of oxidation state, and the stability of -2 oxidation state of the element decreases down the group, because -2 oxidation state is basically shown by those elements which are having the high electronegativity. And as we know that the oxygen is the most electronegative element in the group 16, because the electronegativity decreases down the group due to increase in the atomic size. That's why the stability of -2 oxidation state means tendency to gain the electron decreases down the group. Polonium is the bottom element of the group 16 and it hardly show the -2 oxidation state, since the electronegativity of oxygen is very high. So, oxygen shows only -2 oxidation state, except in the case when it forms the compounds with the fluorine, because fluorine is the highest electronegative element in the periodic table. So, oxygen form the positive state only when it combined with the fluorine. So, for example, when it combined with the fluorine to form the OF2 and O2F2. So, except from these two compounds, the oxygen show only -2 oxidation state. And here the oxidation state of oxygen is +2 and here +1. So, it shows +1 and +2 only in these two compounds, and in all the other compounds counts, the oxidation state of the oxygen is only -2 because oxygen is the electronegative element, and since the electronegativity of oxygen is less than the fluorine, so that when it forms the fluorides, the oxygen has the positive oxidation state. And sulfur, selenium, tellurium and polonium, it show 3 oxidation state, that is the +2, +4 and +6. These oxidation states are shown by the sulfur, selenium, tellurium and polonium. And children, the oxidation state is shown with oxygen, and the stability of +6 oxidation state decreases down the group, and the stability of +4 oxidation state increases down the group. This is due to the inert pair effect, as it is already explained you in the topic group 15 elements, that is the why the lower oxidation state are more stable for the bottom elements and higher oxidation state is more stable for the top elements, and the only reason is that the inert pair effect. Due to the inert pair effect, the stability of +4 oxidation state increases down the group, whereas the stability of +6 oxidation state decreases down the group. This is the reason only for the stability of the oxidation state. After that, the trends in the chemical reactivity, and the trends, the first is when the elements of group 16 combine with different elements. The first is reactivity towards hydrogen. So when the elements of group 16 combine with the hydrogen, it forms the hydride of the type EH2, or we can write it as H2E. Here E is the element of group 16, that is the H2O, H2S, H2SC. So first we discuss about the acidic character of the group 16 elements hydride. Acidic character of the hydrides of group 16 elements. So children, the acidic character of the hydrides of the group 16 element increases from H2O to H2TE. Okay, and the increase in the acidic character can be explained in the terms of decrease in the bond enthalpy for the dissociation of the He bond. That is, E is the element of group 16, that is the He bond strength decreases down the group. That's why the bond dissociation energy also decreases, and therefore the acidic character of the hydrides of the group 16 also increases from H2O to H2TE, because acidic character means the tendency of the compounds to liberate the H plus ion, and any compound can easily liberate the H plus ion if its bond dissociation energy between the H and the element of the group 16 is very low. So since the bond dissociation energy of He bond decreases, therefore the acidic character of the hydrides of group 16 increases from H2O to H2TE. So as the atomic size increases down the group, the bond length increases and hence the bond strength decreases, and this lead to decrease in the bond enthalpy down the group. Consequently children, the dissociation between the hydrogen and element of the group 16 become easy, and as a result of this, the tendency of the hydrides of the group 16 to easily liberate the proton become easy, and that's why the acidic character increases from H2O to H2T. So overall, when we are trying to arrange the acidic character of the group 16 hydrides of the group 16, then how can we arrange this? That is, the H2O has less tendency, then H2S, then H2SC, then in the last H2TE. So in this way we can arrange the acidic character of the hydrides of group 16 elements. So in this way we can arrange, and this can be only explained on the basis of the decrease in the bond dissociation energy of hydrogen and element of the group 16 elements. Next is the thermal stability of the hydrides of the group 16 elements. So thermal stability of the hydrides of the group 16 elements also decreases from H2O to H2TE, because the size of the elements increases down the group, and in this way there is a decrease in the bond dissociation energy of He bond. Okay, and therefore it becomes easier to break down the bonds, and hence the bond can be easily broken down on heating. Therefore the thermal stability also decreases in the order, that is the thermal stability of H2O is more than H2S, then H2SC, then H2TE. So in this order we can arrange the thermal stability of the group hydrides of the group 16 elements, and it decreases down the group, and the decrease in the thermal stability of hydrides of the group 16 is only due to the decrease in the bond dissociation energy of hydrogen and element of group 16. Next is the melting and boiling point. So after the acidic behavior, and here is the thermal stability. This is the thermal stability. It decreases in this order, and after that the next is the melting point and boiling point. Third important property of the hydrides of the group 16, that is the hydrides of oxygen, that is the H2O, is exceptionally very high melting and boiling point due to strong intermolecular hydrogen bonding, and due to that reason only the H2O has very high melting and boiling point. So how the hydrogen bonding is existing in the H2O molecule, that this is the one H2O molecule, and this oxygen of one molecule is associated with hydrogen of another. In this way the another H2 molecule is associated with a hydrogen of another. So in this way the intermolecular hydrogen bonding is taking place, and that is the only reason why the H2O has exceptionally high melting and boiling point among all the hydrides of the group 16 elements, and the only reason is that due to the presence of strong intermolecular hydrogen bonding. So and the other elements of the group 16 do not part in the intermolecular hydrogen bonding, as they are less electronegative and their hydrides are existing in the form of gas. Their physical state is gas, whereas the H2O, due to the formation of this intermolecular hydrogen bonding, this H2O is existing in the liquid form. So however the melting point and boiling point of the hydrides of sulfur, selenium, tellurium are increases down the group due to increase in the atomic number, and when the atomic number and the atomic size increases, this results in the increase in the van der Waals force of interaction, and when the van der Waals force of interaction increases, these hydrides melting and boiling point will also increases. So how does we arrange the hydrides of the group 16 order of increasing melting and boiling point? That is the H2S has less H2SC, then H2TE, and water has very high melting and boiling point. So in this way we arrange the hydrides of the group 16 elements in order of increasing their melting and boiling point. So here a regular trend is observed, whereas there is a difference, that is why H2O has exceptionally high melting and boiling point. The H2O has very high melting and boiling point only due to the formation of this intermolecular hydrogen bonding, whereas the melting and boiling point increases from sulfur to tellurium due to the increase in the atomic size, and the increase in the atomic size results in increase in the van der Waals force of interaction, and in this way the bond becomes stronger and the melting and boiling point increases in this order. After that, children, the next is the reactivity towards oxygen. This is all about the reactivity towards hydrogen. The elements of group 16 combine with the hydrogen to form the hydride of the type H2O, H2E. Next is the reactivity towards oxygen. Reactivity towards oxygen. So the elements of group 16 form two types of oxides. One is the EO2 type oxide and another is O3 type of oxides. And in this, the O3 and SO2 are gases, while O3 and SO2 are gases, whereas the SeO2 is existing in the solid form. So children, as we move down the group, the acidic character decreases in the same oxidation state, and so the SO2 and SeO2 are acidic, whereas TeO2 and POO2 means polonium oxide are amphoteric in the nature. So next we move to the reducing character of the oxides of the group 16 elements. So the reducing character of the dioxides, that is the EO2 type, the reducing character decreases from SO2 to TeO2. It decreases from SO2 to TeO2, and the reason is that it decreases means the sulfur is more stable in +6 oxidation state, whereas tellurium is more stable in +4 oxidation state, and this is only due to the inert pair effect. That's why the SO2 is reducing as +6 oxidation state of the SO2. Sulfur is more stable than the +4 oxidation state, while TeO2 is acting as a good oxidizing agent, as the stability of +6 oxidation state decreases down the group and from sulfur to tellurium, and therefore the reducing character of the dioxides decreases from sulfur to tellurium, sulfur dioxide to tellurium dioxide. Next is this is the overall about the reactivity towards oxygen. So when it combined with the oxygen, it forms two types of oxides, EO2 and EO3, sulfur dioxide, sulfur trioxide. In this, the O3 and SO2 are the gases, SiO2 is a solid. Okay, and the reducing character decreases from SO2 to TeO2. The reason is only that the sulfur is more stable in +6 oxidation state, whereas the tellurium is more stable in +4 oxidation state. That's why the reducing property of the dioxides decreases from SO2 to TeO2, and this is only due to the inert pair effect. After that, children, the reactivity. Third is the reactivity towards halogen. This is very important, reactivity towards halogen. So group 16 elements form a number of halides of the type EX2, EX4 and EX6. Okay, that is the dihalide, tetrahalide and hexahalides. So, and the stability of the hydrides also increases in the order, that is the fluorine compound is more stable, chlorine, then bromine and then iodine. This is the stability of halides. Among the hexahalides, hexafluorides compounds are only stable halides. Means when the group 16 elements combine with the fluorine atom, then only it results in the formation of the stable hexahalides. And these hexahalides are gaseous and they having the hybridization for means that is the EX6 are gases and they have the hybridization that is sp3d2, and the geometry of the complex is octahedral geometry. So when we arrange the relative stability, it is found that it decreases in the order, that is the SF6 is more stable than selenium F6, which is more stable than TeF6. So it decreases in this order. Next is important about SF6. Why SF6 is thermally stable and chemically inert? This is only due to the structure of the SF6. In the structure of SF6, you see that there is 6 fluorine atom. The sulfur is surrounded by 6 fluorine atom, and due to this geometry, it is found that the SF6 is chemically inert and inreactive, and it is thermally stable due to fact that all the 6 fluorine atoms sterically protect the sulfur atom from the attack by the reagent to such that any extent that it make it thermodynamically more stable, more favorable, like the hydrolysis reaction do not occur in this, because the sulfur is sterically protected by the 6 fluorine atoms. However, as the size of the central atom increases, the steric hindrance decreases, and hence the hydrolysis become easier. Next, about the monohalides. This is about the hexahalides. Next is the monohalides, and in this monohalides, that is the S2F2, S2Cl2. These are the important monohalides, and they are dimeric in the nature, and they undergo disproportionation reaction. That is, when the Se2Cl2, when it undergo the disproportionation reaction, it gives SeCl4 plus Sc. Okay, so in this way it undergo the disproportionation reaction. After the hydrolysis disproportionation, this is the monohalide, and after this disproportionation, it gives the tetrahalides. Okay, next is all the elements except oxygen form dichlorides and dibromides, having the hybridization, that is sp3 hybridization, and they have the tetrahedral geometry. Among the tetrafluorides, the SF4 is a gas, SeF4 sulfur compound is gas, SeF4 is liquid, okay, and TeF4 is a solid. Next is the TeF4 is solid. Okay, so these are about the tetrafluorides of the group 16 elements, and they have in the hybridization sp3 dehybridization, and sp3 hybridization has the shape trigonal bipyramidal structure, and due to the presence of one lone pair of electron which repel each other, which repel the bond pair of the electron, that's why all the bonds in SF4 are not equal. Important compound of the group 16 in this first is the dioxygen. Children, you can see in the slide, that is, the dioxygen can be prepared in the laboratory by the following ways. First is by the decomposition of oxygen-rich compounds like chlorate, nitrates and permanganates. You see that, children, that is the chlorates and permanganates undergo the decomposition, it gives the oxygen along with the other compounds. Next is preparation is by the thermal decomposition of the oxides of metals, low metals in the electrochemical series, and higher oxides of some metal. And these are the preparation method by the decomposition of oxides of the metals. Next is the decomposition of hydrogen peroxide into water and dioxygen using catalysts such as the finely divided metals and manganese dioxide. So in this way, the hydrogen peroxide undergo decomposition to give water and oxygen. And another important preparation of dioxygen, that is, it can be prepared from water or air. As we know that in the water and air oxygen is present. So on large scale we can prepare the dioxygen by the electrolysis of water, which leads to the release of hydrogen at cathode and oxygen at anode. Next is the properties of dioxygen. Children, this is the slide of the properties, and here these are the important physical properties of the dioxygen. So children, you can see the slide and take the snap of that. Next is the uses of dioxygen, where we use the dioxygen in our day-to-day life. This is the slide, so you can take a snap of that also. So children, that's all for today, and next continue in the next class.